Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 17, Liquids and Solids, Part 4. Here are our objectives for today's video. Pause here. I would include the picture, but it doesn't have to be quite as large. So we've discussed alloys. These are homogeneous mixtures of metals, but now we're going to discuss the different types of metals or types of alloys. So when you have two things that are being mixed together, say Cu and Ag, and they've got a pretty similar atomic radius, I'd say a cutoff of a 15% difference between the two, but I'm not going to test you on that 15%. Whatever metal is added is going to substitute in. So if you take a look at the picture on the left, those darker circles, they've just taken the place of a white circle, but the actual arrangement has not changed. This is called a substitutional alloy because one metal is substituting for another. Both of these types of alloys are going to result in things being a little bit harder, more difficult to break, and there are reasons for that that have to do with intermolecular forces. And then when metals have a very different atomic radius, say in the case of stainless steel, iron is so much larger than carbon. Those carbon atoms just substitute in, or don't substitute in, rather, they actually go in between what would be the normal lattice, and that is called an interstitial alloy. So both substitutional interstitial alloys really add another layer of intermolecular forces that make it difficult to break a substance. Even in a substitutional alloy, those slight differences in atomic radius really make it difficult to break, hence why alloys are so much stronger and harder than metals. Also, you tend to see a decrease in conductivity most of the time as well, because it is not as easy for those electrons to flow when the lattice is not as ordered as it normally is. Pause here. You don't need to write the question down. All right, so let's take a look at this question. This is talking about alloys. It tells you in the table that they're all pretty similar in metallic in the radius, which is just the atomic radius. The melting point is unlikely to have a huge difference, whereas in the oxidation states really shouldn't matter at all because an alloy is completely non-charged. All right, so let's look through the question. So let's just eliminate things that we need to eliminate. So A, I am just going to eliminate off the top of, just eliminate it right away. B, I also just don't see that melting point is relevant, so I'm going to eliminate that. And then D and C, these are things that we're going to look at. So the AU-Cu alloy is harder and stronger than the AU-Ag alloy. So I'm going to look for things that would support AU-Cu being harder to break. So if I look at C, that makes sense because the Cu atoms are smaller than the Ag atoms. They're going to affect the displacement of atoms, what we were just talking about in the slide prior. And then I just don't see D as being a very relevant answer. So Cu atoms, while there might be a difference in polarizability than Au, it's not going to be huge for one thing. And then polarizability doesn't really play a huge role in metals. So that's why I'm going to go with C. Pause here. So we talked about semiconductors last year where we were talking about metals, metalloids, nonmetals. And these are things that conduct electricity above a critical temperature. You should know that silicon is a semiconductor. But sometimes we want to increase the conductivity of a semiconductor, and we're going to add a small quantity of a different atom. So if we add the addition of those atoms is called doping. So if you have N-type and being negative type semiconductors, an atom that has an additional valence electron is added. That additional valence electron just makes it easier for the current to flow. And then P-type semiconductors, an atom with one less electron is added, one less valence electron, and that also increases the current. But the N and the P-type, they will typically create currents in opposite directions from one another, which is why you could have NP junctions where you have an N-type and a P-type semiconductor in direct contact with one another, and these can be used to control the direction of current in some sort of electronic device. I have not actually seen any practice problems on these in more recent AP exams. It doesn't mean that there won't be. I just haven't seen them, but we do have one practice problem from a couple of years ago that we'll be able to look at in class. Right, here are the practice problems for today's video. Thank you so much for watching and have a great night.